All right. And here's the PowerPoint. Let's start the slideshow at current slide. All right, here we go, finally. Okay, why did it go back to that? Okay, here we go again. Okay, you're the culprit, okay? Okay. There we go. All right, these things, these boards are easily to trip over. All right, before we get going on the 2.2, did want to let you know this. I have, there are some changes to office hours this week, but not, the first one is not really a change. But now that we're in the second mini term, I haven't gotten this up. It's on my locator card on my door. My office hours have shrunk like crazy because I'm here late on Tuesday, Thursday evening. So my Monday, Wednesday office hours, I lose some. Technically, I'm supposed to be off campus at 2 o'clock. Seldom, if ever, will I be off campus at 2 o'clock. However, tomorrow, I do have to go to the Birmingham campus for a meeting at 3 o'clock. Or at least that's when I think it is now. That's the last I've seen from anyone. So I will be here. My last class ends at 1:55. I'll leave sometime between 2 and 2:30. So it's actually after my office hours are supposed to be over anyway, but normally I'm here. But then on Friday, I usually do have office hours on the Birmingham campus, 7:45 to 11:45, not this Friday at all. I'm starting a new round of treatment, and they say it'll be there at 7:30, and it'll last about 7 hours. So I will not be back on campus at all on Friday. So I will not be on campus Friday. So if you need to see me, get it done Monday through Thursday of this week, or Tuesday through Thursday of this week. And by the way, next week, since this is the first treatment, they're doing a reduced treatment. And then if I don't have any adverse reactions to that, then they give me a full treatment on next Friday. So next Friday I'll be going to 7:30 in the morning until the Jarian is here. So I know those 2 Fridays I'll be out. All right. Any questions on anything we've done so far? And again, since more people have come in, let me say this again. If you haven't finished the test, please get with me and try to get that completed as soon as you can. If you have finished the test but don't see your grade on Blackboard, that means I couldn't tell if you were finished or not. So let me know if you want that grade to be posted. Don't post them until I'm sure that that is what the last you're going to do on it. All right, any questions? Okay. So we're continuing chapter 2, which is polynomial and rational functions. Y'all know what polynomial functions are, right? Functions with many names. In other words, many terms. And that many could be as few as 1, okay? Okay, polynomial functions. That's what we're dealing with to begin with. And in section 2.1, we dealt with what kind of polynomial functions? Predominantly. Oh, it was so long ago. Okay, graphing what kind? Okay, we did talk a little bit about linear, but we didn't spend a lot of time on linear. Next, parabolas, which are second-degree polynomial functions, which are quadratic functions. Now we're going to look at polynomial functions of higher degree. Okay? Okay. Now, what we'll do is use transformations. They love transformations to sketch graphs. They really love graphs of polynomial functions. We'll use the leading coefficient test. Now, I don't know if you realized it or not, but we were using that with quadratics, weren't we? What did the leading coefficient tell you about quadratics? Say again? Positive or negative, and what does that tell you? Opening up or down. And the leading coefficient on quadratics determines what we call end behavior. What happens when the x is very large negatively, very large positively? Of course, quadratic, they're either going up or they're going down, and that depends on the leading coefficient. Well, for a higher order polynomial functions, we still look at that leading coefficient to determine the end behavior. what's going on in the long run. Very positive, very large positive and very large negative numbers. Okay? And we'll find and use the real zeros of polynomial functions as sketching aids, because we love to graph our functions, right? Finally, we'll use the intermediate value theorem to help locate real zeros of polynomial functions. A little tedious, but it certainly is a help. Okay, let's start with good old graphs of polynomial functions. This section will study basic features of the graphs of polynomial functions. And here are two features coming up. We're going to hit one on this one, and we'll hit a one, I think, on the next slide or somewhere pretty soon. If not, I'll tell you what it is. Every polynomial function is continuous. What does that mean? Say again? Say again? Okay, never ends, exactly, in either direction, in the middle, or anywhere. That means essentially that the graph of the polynomial function has no breaks, no holes, no gaps. This could be, doesn't have to be, but this could be the graph of a polynomial function. So one characteristic, continuous. There's another characteristic that we see here, but we haven't mentioned it yet. We'll come up with that later, okay? But those are continuous functions, always a polynomial function. Could this be a polynomial function? No, because it has a break, it has a gap, okay? Discontinuity there at whatever value x this is. This could be a piecewise defined function. This side could be polynomial, and that side could be polynomial, but overall, it's not a polynomial function because it has that. This is a piecewise defined function, not continuous. Couldn't be a polynomial function. All polynomial functions are always continuous. The second feature is that the graph of a polynomial function has only smooth, rounded turns or curves in it, okay? There's never any points, cusps, or certainly breaks or other things like this. All your turning points are smooth, okay? So, like good jazz, okay? Polynomial functions are smooth and continuous. The two features of polynomial functions, okay? Now, we'll pick out other features a little bit later, clues to features anyway. Like I could, just looking at that function, I could tell you something, and we'll get there later. No reason. Jump ahead. Is that a polynomial function? No, it isn't. It has a sharp point on it. You know, it's a continuous function, but it is not a smooth function. This happens to be the absolute value function. This side is a polynomial function, linear. This side is a polynomial function, linear, but it's not a polynomial function because it's not smooth. It is continuous, but not smooth. Sharp point at 0, 0. When you get into calculus, there's another little bit cleaner way to define smooth, but right now, that's not smooth. Okay. The graphs of polynomial functions of degree greater than 2, 2 would be quadratics, anything greater than 2, cubics, quartics, and on up, are more difficult to analyze than the graphs of polynomial functions. In 0 degree, those are straight or horizontal lines. 1, degree 1, or any other straight lines, and degree 2 are parabolae. Okay? So beyond that, it's a little harder to analyze. Okay? Those are, you can tell everything you need to know about them. So we'll have to do a little more work to figure out what to do with polynomial functions of degree 3 and higher. However, those features presented in this section, coupled with your knowledge of point plotting, intercepts, y'all know what intercepts are, right? What two types of intercepts do we have? X-intercepts and Y-intercepts. What's true about an X-intercept? Every X-intercept. It's true about every point on the X-axis. There's one feature they all have in common. Y is equal to 0. Now what's the feature about a Y-intercept? x is equal to 0. Yes, you know about those. Those probably, certainly the y-intercepts are really easy to calculate. The x-intercepts, they may take a little more work, but usually we can do it. Symmetry. Remember, even and oddness and that kind of stuff, reflection across x-axis, y-axis, that kind of stuff. Okay? You should be able to make reasonably accurate sketches by hand. Okay? You don't have to have graphing calculators. They may make you feel good and give you a good feel. Yes, I did see that right, or whatever. Okay? But it's not going to be absolutely necessary. Nice to have, but not necessary. The polynomial functions that have the simplest graphs are monomials in the form of f of x is equal to x to the n. What do we used to call those back in chapter 1, section maybe 1.4 or 5? No. 1.7, I think it may be. I don't know. Somewhere back there. 1.6, I believe it was. What do we call a function like this? Simplest form of these polynomial functions. Those old folks. Parent functions. Never mind. Bad clue. Okay. All right. Where n is an integer greater than 0. Now, what do we mean integer? No fractions, decimals, and that kind of stuff. Greater than 0 meaning always positive. That's what makes a polynomial function. All the exponents have to be positive integers. This is the simplest form where you just have n is a positive integer, and that's the only term. Okay? Now, you've already seen most of these graphs because we did them earlier. But here's figure 2.9. You can see that when n is even, here is a clue. Like n equal 2, that's going to be your good old parabola, right? When n is equal to 4, y is equal to x to the 4th. Okay, a couple features about every one of the graphs. Let's go back one page. Okay, every one of the graphs that is in this form. When x is equal to 0, what's y? 0. When x is equal to 1, y is equal to 1. Okay. Now, depending on the sign, the even or oddness of n, when x is negative 1, y is equal either plus 1 or negative 1. One or the other when x is negative 1. So those 3 points you almost always know. 0, 1, and generally it's easy to figure out minus 1. Okay? Now, so 0 is the same. Plus 1 for an even power here, when n is even. A plus 1 raised to any power is going to be 1. And a minus 1 raised to any even power is going to be 1. So those 3 points are always going to be on there for even functions. Okay? Even parent functions. Okay? Now here's where the difference comes. Outside of and near plus and minus 1, the graphs of x to the 4th, the quartic function, is steeper near plus or minus 1 on both sides, and near 0 is flatter. Okay? So the parabola comes down, kisses, and goes up. This one comes down and lingers a bit and goes up much more sharply. Okay? If you did x to the 6th, even sharper here, flatter here, sharper there. X to the 18th, I mean, you almost get a tunnel there, you almost get pretty sharp corners. Never sharp, they're always curved. They're polynomial functions. Okay? The x-intercept and the y-intercept is 0, 0. Now, when n is odd, notice what happens. I hope you remember the cubic function. Our 3 points that are always the same. When x equals 0, y is 0. X equals plus 1, y is plus 1. But when x equals minus 1 and the n is odd, y is also minus 1 because the odd number of negative signs is always negative. So all of these functions go through these 3 points. When when the n is odd, they go through those 3 points. Parent functions we're talking about. Now, what's the difference? Okay, let's back off and do one more that's not really usually included here, but it definitely is. When n is 1, what do we have then? Y is equal to x. What's that function? It goes through -1 plus 1, 0, 0, plus 1, plus 1. The identity function. It goes through these same 3 points. And notice, when x is negative, y is negative. When x is positive, y is positive. For odd things. Here for even parent functions, x positive, y is positive. X negative, y is still positive because you're raising it to an even number of powers. Okay? So, for y is equal to x, when n is 1, it's a straight line through there. The cubic function, it comes up and briefly hangs around 0 and then goes on up. When n is equal to 5, steeper around plus or minus 1 and flatter around 0. Just like we saw back here, except it's on the other side down here. N equals 7, x to the 7th, even steeper here, flatter there, steeper there. N equals 19, really steep here, really flat there, and really steep there. It goes up really, really quickly past plus or minus 1. Does that make sense? Even functions look like this, odd functions look like that. These are the parent functions. We call them the power functions. All you're doing is raising the variable to a power. And we're only going to use positive integer powers. Even, up and up, odd, up and down, down and up. Make sense? Okay. Moreover, the greater the value of n, the flatter it is near the origin. I've already said that. And the steeper it is near plus or minus 1. Okay, they don't say that, but it's still true. All right, here's what we're going to do. Sketch the graph of each of these functions. This is example 1, page 125. Now, they've done something to it, haven't they? What is that they've done? No longer just a power function. They have negated it. So what is that going to do to us? Okay? Now, I'm going to kind of model here your thinking process. First thing I would note is, thank you. First thing I would note is, what's your exponent? 5. What does that tell you? Say again? It's an odd function. What does that tell you about the graph of it? Okay, it's like a cubic. Very good. A little flat around the origin and steeper outside. But what does this minus sign do to it? Say again? It reflects it across the x-axis, absolutely. Because this is the y value, the x to the 5th, and this negates it. So whatever you were having there, now it'll be down there. Whatever you were having here, it's going to be up there. Reflects it across the y-axis. So can you give me a few points there? The easy ones are? Second? Okay, when x equals 1, what is your y equal? Second? Really? -1, that minus sign negates it, okay? It's down here now, okay? Another easy one. Second, 0, what is your y value? 0, got it. -1, what would your y value be? +1, because normally an odd number of signs, and it still is true, odd number of signs, odd number of -1s here, if you plug that in, will give you a minus, but this makes one more, so that makes an even number of minus signs, so that's going to make it positive. Okay? And from there, you don't have to do any more. In fact, it's pretty hard to, because they go up so rapidly and stay flat so much more and go down so rapidly. That basically is what it looks like. Right? Now, you could have plotted the parent function first. Y is equal to x to the 5th. You can see what that looks like and flip it over. I didn't quite make it through the origin, but you get the general idea. All right, how about that h of x? What color you want that in? Say again? I couldn't hear. Blue, okay. Light or dark? Light, okay, here we go. Light blue. Here is our function, and there is your head, right? All right. What's different about, for some reason, it didn't seem to take it. There we go, okay. What would be your parent function here? A little louder. It looks like a parabola, but it's actually the coordinate function. The parent function would be x to the fourth. Okay? Let's do that one then. You want that in light blue or you want that in a different color? Light blue. Okay. To get that coordinate function, that would be this one. Let's call it h1 of x. That's not the same as our h of x. That's equal to x to the fourth. How would I plot that one? Give me some points. Okay, I saw the air picture showing up. Okay, very good air artist, by the way. Okay, my congratulations. Okay, all right. 0, 0. 1 what? 1, 1, because this is even, and -1, 1. And then after that, they get really big really fast. So again, very steep here, very flat here, and very steep there. That basically is what it looks like. Now, what's different about H from what I called H1? The what? A horizontal shift. Huh? To the left. You're absolutely right, because with X's, everything's backwards. So we go left one. What color you want this one? Red? Okay. All right. Light red or dark red? Dark red. Okay, here we go. We're going to shift everything to the left one. So this 0, 0 becomes -1, 0. The -1, 1 becomes -2, 1. Okay? And the +1, 1 becomes 0, 1. Here is our function, goes up very sharply, comes down sharply here, flattens out here, and goes up sharply there. There it is. H of x is this red function here. Do you see how that works? Second? Because you added 1 to the x. Okay? And you might think, wouldn't that go to the right? No, anything dealing with the x, do backwards. So that's just to the left one. And here's a way to check. What would be an easy variable for x, a value for x to put in here? 0. Okay, when you get 0, what do you get? 1 to the fourth is 1. There it is. Another easy one. 1 would be a little harder, because that's going to be 2 to the fourth, and that's a huge number. But -1 plus 1 is 0. 0 to the fourth is 0. So sure enough, there you are. Shifted to the left one. That one shifted to the left one. This one shifted to the left one. Go to the next one. -2 plus 1. -1 to the fourth power is 1. So that's -2, 1. Sure enough, there it is. Shifted everything to the left one. Does that answer your question? Yes, you're absolutely right. If that was x -1 to the fourth power, yep, shifts to the right. That big U shifts over there to the right one. You're absolutely right. Now, if there had been a +7 after this, what would that have done? It goes up from where you shifted left, then you go up 7 off scale here. But if it had been a -7, now see the y's, they go in the direction you expect. The x's are always opposite. Those contrary x's. Okay. That's how we did it. Let's see how they do. I'm going to erase the ink and see what they got. Because the degree of f of x at a negative x to the fifth. It's an odd function. Its graph is similar to the graph of y is equal to x cubed. Now, they didn't draw that, but that would have been like that, okay? Except for x to the fifth, been steeper on the plus and minus ones and flatter near zero. And in figure 210, note that whatever you get there from the without the minus sign, you flip it across the x-axis, and that gives you everything reversed on the values. You negate every value. Note that the negative coefficient has the effect of reflecting the graph in the x-axis. I like to say across the x-axis. So, make sense? Notice it's flat near zero, fairly steep, plus or minus 1. Sorry. The graph of h of x, which is x plus 4, x plus 1 to the fourth power, the one we were just talking about, would have been like a parabola here, going up because it's a positive sign here, but it's been shifted to the left one because of that plus 1 there, and then it still is going up. Does that make sense? All right, good deal. And you can always check. If you're not sure, plug in a few values and you'll see, yep, it looks like it's moved over there. All right. That was example 1. There is a checkpoint there. The checkpoint has 4 things to look at. A little more involved than what we were just doing, so please, I'd say, as soon as class is over and you don't have another class, you can get somewhere, try to do those checkpoints. And if you can't figure them out, the audio-video solution is available at larsonprecalculus.com. So now we move to the leading coefficient test. We've kind of been talking around it all along. Now let's sort of formalize. In that first example, you note that both graphs eventually rise or fall. This is another feature of polynomial functions. In the long run, they're going to some infinity. Every time. Polynomial functions, you get x is large enough, they're either going to be going very, very large positive or very, very large negative. Get x is small enough, very, very negative, they're going to be very negative or very positive. The y is going either way up or way down. So the graphs eventually rise or fall without bound. I mean, they may do some jiggling in the middle and curves like that, but in the long run, they're going somewhere, okay? Toward infinity, okay? As x moves to the left or to the right, far enough, they're going to infinity. Whether the graph of a polynomial function eventually rises or falls, determined by 2 things, and they're really all tied up in one, okay? Determined first by the function's degree. Now, what the degree is isn't really as important as whether it's even or odd. Okay? That's the big thing. What is the degree? Okay? Is it even or odd? And by the leading coefficient. Is that positive or negative? And guess where the function's degree and leading coefficient both live? In the leading term. Okay? The leading term is always the term with the greatest degree, and it's also the term with the leading coefficient. So when they say leading coefficient test, I like to say leading term test. Look at the leading term, the term with the greatest degree, largest exponent, and look at what its coefficient is. That's going to tell you what you need to know in the long run. It won't tell you what's happening in the middle. We'll do that later. That tells you what happens for large x's and very, very small x's. In other words, very, very negative x's. They call it leading coefficient test. I call it leading term test. So here's what's happening. As x moves without bound to the left, being very, very negative, or to the right, going very, very positive, the graph of the polynomial function is always going to some infinity. Always. Okay? Now, here's your f of x. A sub n, that's your leading coefficient. x to the n, that's the degree, and then they decrease in n's, and the a that just tells you different coefficients possibly or whatever, until you get a to the sub 1, x to the first power, a sub 0, x to the 0 power, which of course is 1, so it's just a sub 0. Eventually, they rise or fall in this manner. It doesn't matter what these terms are doing. That messes with it in the middle. And that's important. But what happens in the long run is what happening to that first term, leading term. When this n is odd, what does that tell you? What's happening in the long run? When n is odd, yes, they're going in opposite directions. You don't know which direction, but they're going opposite directions. Anytime that leading degree, the degree of the leading term is odd, then they're going to be going in opposite directions. Okay? So when n is odd, either as x goes to negative infinity, f of x or y is going to negative infinity, and x going to positive infinity, f of x going to positive infinity. Or, if n is odd, as x goes to negative infinity, f of x could be going to positive infinity, but if that's the case, then as x goes to positive infinity, f of x is going to negative infinity. Okay. Now, when we're looking at n behavior, notice here what we're doing. These four features, always the same. Okay? You're looking as x goes one direction, what's y doing? When x is going the other direction, what's y doing? That's going to define your n behavior. And guess what? Every one of these numbers is an infinity. Okay? So when you have this on a quiz or have this on a test, you can fill in most of the answer just by looking at it. If you're looking for n behavior as x going to negative infinity, put your minus sign with that one. As x going to positive infinity, leave the sign off of that one. The other two, the y's are going to be infinities. We just don't know whether plus or minus sign. So all you have to determine is what sign to put with the others. So 1x is going to be negative infinity, 1x is going to be positive infinity, the two y's are going to be infinities. You just have to figure out the sign to them. It's a pretty simple process. Okay? If the n is odd, you know those two y's have opposite signs. Okay? Now, if that leading coefficient, see, that's what the degree of the leading term tells you. Opposite directions, same direction, whether it's odd or even. Okay? Now, what the a sub n, the coefficient of that term tells you, is which way it's going. Okay? And here's, to me, the easy way to do this. If that a, remember, in the long run, this is ruling the roost. It's controlling the show, right? Those other terms, lower powers of x, they can't compete with the big one. This is Big Daddy here, okay? It's going to determine what happens in the long run. These will mess with the stuff in between, like all this stuff, but in the long run, this one tells you what's going on, okay? Now, if that a sub n is positive, what I usually do is pick some number. It doesn't have to be very big. My favorite is 10. Not a very big number. It's not anywhere close to infinity. But if you have 10 raised to some power, and remember your n is always positive, okay? 10 raised to any power, positive or negative, is going to be some huge number, like 1,000. No, let's see. Yeah, 10 raised to the third power would be 1,000. 10 raised to the 17th power would be 17 zeros after your 1, with all those combinations. It's going to an infinity. That would be a plus infinity. Now, if this a is negative, that takes that very large number and flips it over and makes it very negative. Okay? If this is an odd function and the x is going very negative, like a negative 10, what happens when you raise it to the nth power? It's going to be very big or very small, and then if the a sub n is negative, it's going to flip it from whatever you thought it would be. So just play around with things like this. So if a is positive, it's going to be down on the negative side, up on the positive side. If the a sub n, that leading coefficient, is negative, it flips it over. So when x gets very large negative, the y is going very large positive, the x going very large positive, y is going very large negative. If that n is odd, they're going in opposite directions. The a tells you, the sign of a tells you which direction that is. Not that hard, right? Now, secondly, what if n was even? What does that tell you? If the n, the exponent is an even exponent, leading exponent, the maximum exponent is even, what does that tell you? Same direction. It's either on the up and up or down and down, okay? Odd, opposite directions, even, same direction. And guess what? If that a happens to be positive, then you raise 10 to a positive power, it's going very large. A is positive, it's still going very large. Raise negative 10 to an even power, very large. And if A is positive, still very large. But if that A happens to be negative, it takes those large values and flips them over and makes them very large negative. Still large. Notice here, 1x is negative infinity, 1x is positive infinity. Those are easy. You can plug those in every time. Then the question is, what are your y's or your f of x's? They're both infinities. Always, okay? But what are the signs? That's all you have to figure out. And if the n is even for that leading term, they're the same. And if the a is positive, they're up and up. If n is even, they're the same. But if a is negative, it's down and up. So you can just put the minus signs in here and here. Positive signs, leave them alone right there. See how it is? It doesn't matter what's happening in here. Those are those intermediate terms. Yeah, we'll figure those out later. We're looking for in behavior now. Easiest thing to do first. Okay? And we'll do that on graphs much later in the chapter as well. So, all it says is describe the right-hand behavior and the left-hand behavior of the graph of these functions. Okay? A. What do you reckon's going on with A? Say again? What is going down? Which way? We look at two ends. Let's start with the right-hand end. Is that what you're saying? The right-hand end, you're absolutely right, is going down. Pick a large x, like 10, raise it to the third power. That becomes 1,000, okay? And the minus makes it a negative 1,000. That's going downhill really fast, okay? Larger the x, the further down it goes, okay? So sure enough, the right-hand behavior on this one is to negative infinity. How would we express that? You can fill in the blanks almost to begin with. I like to start with this way. The book does it otherwise. As x approaches blank, f of x approaches blank. As x approaches another blank, f of x approaches some other blank. Okay? Can you tell me what to put in the x blanks? Say again? One of the x's going to negative infinity, and one of the x's going to positive infinity. Guess what? You get 2 points right there. I mean, you get value on that. All you have to do is remember that, okay? Now, what symbol is going to go in both of the f's? Infinities, okay? All you have to do then is determine what signs to put with them, okay? So as x is going to negative infinity, what's your f doing for a? It's going to positive because normally it'd be going negative, so that goes to positive. We got that done. And as x goes to positive infinity, what's happening to the f then? It's going down. It would be going positive, except you have a minus sign in front of it. Okay. When x is going to positive infinity, some large value of x, pick 10. Okay? 10 cubed is 1,000. But then you negate it and it becomes negative 1,000. All right, this adds a little bit, but it doesn't add much. So this is plus 40. Huh? This is the answer for the right-hand side. Okay. For the left-hand side, this is the answer. Right-hand side, you decide what sign to put in it, and someone decided you put a minus there. Okay? You can put your infinities there to begin with. X1's going to be positive, 1's going to be negative. Doesn't matter which way you do it. And then for the y's, or f of x, you decide what sign goes with it. 1 was positive, 1 was negative, because this was an odd x1. Okay? Can we do the same thing with b? Okay? You want b in a different color? What color? Blue for b? Is that fine? Okay. We'll pick a dark blue this time. This will be as x goes to blank, alpha of x goes to blank, as x goes to some other blank, alpha of x is going to some other blank. What goes in the blanks? Infinities in every one. You know that. This is in behavior of a polynomial function. Later we do rational functions. Yeah, you got to do other things to it. But here, polynomial function, every one of those is an infinity, even if they're ugly infinities. Okay? Ooh, that's terrible. Okay. Now, the x1's going to be positive and 1's going to be negative. Okay? You got that done. The x's are done now. Okay? Now you have to figure out what the signs of the y's are going to be. You know they're going to infinities, you just don't know if they're up or down. What you reckon b is for the y's? Up and up, exactly, because this is an even exponent, so they're going in the same direction. Positive sign, they got to go up. No choice going up, so that's absolutely done right there. You got it done. Okay, how about C? What will you make C? What color you want C to be? Green, okay? All right. And we're going to start this as x goes to something. Alpha of x is going to something as x goes to something else. Alpha of x is going to something else. Okay? What goes in all the blanks? Infinities, okay, because these are polynomial functions. This is in behavior we're talking about. The x's are going to either positive or negative infinity. So I just gave it away. What do you put for the x's? 1 positive and 1 negative. Okay, now all you have to do is figure out the signs of the other two infinities. Okay? What would it be here? Is x going to positive infinity? What would this be going to? One goes negative, 1 positive. You got that right. Huh? Okay. Because the odd endpoints are going in opposite directions, but what sign goes for which one? As x goes positive, that's what you chose first. What's your alpha one? That's what? Stays right there. It's positive. Because if this goes large, like if x is 10, that's not very large. If that's 10, 10 to the 5th is 100,000. Okay, positive. Way up there. Okay? And if x goes to negative 10, that's going to be, because it's odd, negative 10,000. So that sign over there goes negative. Does that make sense? This isn't that hard, right? All right, let's see what they do. I bet you they actually graph it, but let's see if they do. I'm going to clear the ink, and let's see what they do. Ah, they do graph it. Don't have to, but they're going to. Because the degree of that first one, this is A, they don't count there, it is A, is odd, the n is odd, you know they're going opposite directions. Because it's minus, that means when x is going negative, y is going positive. And when x is going positive, y is going negative. Because that minus sign flips it across. Now, do they actually write it down? No, they don't. Not yet. They may later. Here's the B one. What's happening with this one? Because degree is even, they're going in the same direction. Because the sign is positive, they're both positive. Up and up. this stuff in here, that determines what this is going on. This determines what's going on in the long run for large x's. Okay? Now, something you tell me about this function. What do you notice about that function? The what? Okay, it makes a W, and that W is symmetric. Why is that true? Even function. Let's go back to that last one, the previous one. What do you notice here? Odd function because both of the exponents are odd. So this is reflected across the origin. Okay, so that wasn't part of the question, but it is. And that, shows you they got to be going opposite directions here, same directions there. Now, not all even functions, that it's all the leading term that matters, but these functions happen to be even and odd. So here's C. Goodness, they did this to us again. What do we notice here? It's an odd function, so it's reflected across the origin. Okay? But all we're really interested in is this. That's also odd, because it's an odd function, but it would have been odd even if those had had squares in it. It still would have been, this would have been odd. The function would have been, but this would have been. And this would tell you that for x is very large negative, then f is very large negative. X very large positive, f very large positive. So that's what that shows you. Now, do they ever write it down? Okay, no, they don't. In example 2, note that the leading coefficient test, I like to call it the leading term test, tells you only whether the graph eventually rises or falls to the right or left. It doesn't tell you what's happening in the middle. Other characteristics of the graph, such as the intercepts, minimum, maximum points, they must be determined by other tests. And that's really what most of the rest of the chapter is going to be doing, is looking at these other features. So the first thing we're going to look at are the real zeros of the polynomial function. Now you have to remind me, what is a zero of a polynomial function? How do we get it? You set the function equal to 0 exactly, and then try to solve it. Okay? And generally that solving is going to involve, what's the F word? Factoring if you can, whatever tricks you can use to do it. And the rest of this chapter, until we get to section 6, is going to be showing you different things you can do to these functions. So we're first going to look at real zeros. Now the zeros of a polynomial function have another name. Anyone remember what they are? If it's where the function is equal to 0, what is the function? F of x, what's that always equal to? Y, why not? Okay, and then if y is equal to 0, what is another name for those zeros of the polynomial? X-intercepts, exactly. So that's what we're doing now, is looking for x-intercepts, or the real zeros of the polynomial functions. Now, here's a hint. Let's go back to some of those graphs. All right. What was the degree of this polynomial function? Yeah, but what number? 3. How many zeros does this one happen to have? 3. 1, 2, 3. Is that guaranteed? No, but it can't ever have more than 3. It's going to have 3 or fewer, always. Okay, that next one, what's its degree? 4. How many zeros does that happen to have? 4. 1, 2, 3, 4. So it's always going to have 4 or less. Can never have 5 or 7 or 15. Limited to whatever that degree is. May not reach that, but it's limited to that. Now, how about this one? What's its degree? 5, but how many zeros does it have? Only 3. Okay? So, don't have to have 5, but it never can be more than 5. 5 would be the max. That's what this next thing is telling us. It can be shown that for a polynomial function of degree n, the following statements are true. the function has at most n real zeros. Okay, let's back that up one more. What if the function has degree 1? What does that function look like? What kind of function is it? Degree 1. Linear function. So what does this graph look like? A straight line. Okay? Now, it always has curvature to it, because if it didn't have curvature, it would be a horizontal, not curvature, a slant to it. If it didn't, it'd be a straight line, a horizontal line. The horizontal line, what's its degree? 0, because it doesn't have an x in it at all. It's just a constant. So, any line that has a non-zero slope, how many times is it going to cross the x-axis? 1. 1. Can't ever cross more than 1. So you see, even for a degree 1, then it's going to have at most 1 real zero. And at degree 0, how many times does it cross the x-axis? Never. 0. Now, that's why they tend to say f of x equals 0 is not really, they don't count that, because every point is 0 then, so it has an infinite number. So we usually leave that one off. Okay. Now, not just that. Let's go back and look again. What's the degree of this function? 3. How many turning points does this have? What do we mean by turning points? When it changes direction. 1, 2. At most 2. Always n minus 1. Let's see if it worked for the next one. What's its degree? 4. How many turning points? 1, 2, 3. N minus 1. Absolutely. At most. How about this one? Degree 5. At most 4. This one only has 2. Remember, it doesn't have to have 4, but it can't have more than 4. Okay? Good deal. So there's the second feature. A graph of F has at most n minus 1 turning points. If it's a nth degree polynomial, then it has at most n minus 1 turning points. Turning points also called relative minimum, if it's now turning here, or relative maximum if it's up there. Okay? There are points at which the graph changes from increasing to decreasing, or decreasing to increasing. Turning points. Finding the zeros of the polynomial function is one of the most important problems in algebra. So that's what we're going to spend some time on now. Okay? Let me make sure I'm not skipping anything. Yeah. There is a strong interplay between the graphical and the algebraic approaches to the problem. I think we've already seen those. When f is a polynomial function, what are two features of a polynomial function? Jazz, smooth, and continuous. Okay, those are two features. The other feature you should know too is that in the long run they're going to an infinity. Okay, you got to know that one too. Okay, so when f is a polynomial function, it's going to be smooth, it's going to be continuous, and in the long run it's going to some infinity somewhere. And a is a real number. The following statements are all equivalent. And we've already sort of hit on this one. X equal a is a zero of the function. Okay? That's one statement. If that's true, all these others are true as well. What did we also say? X equal a is a solution of the polynomial equation, setting that f of x equals 0. Because the zeros are polynomial where the function is equal to 0. So if x equal a is a solution to that, it's a 0 of the function. And guess what else it is? A0 is then an x-intercept. We mentioned that one. Here's the other one. X minus a would be a factor of that polynomial f of x. And why is that true? Remember, if we set that equal to 0, then the first thing we would do to this is factor it, right? F-words. Then we set each factor equal to 0. So if this is equal to 0, 0, that told us that x equal a is a solution. So now we go the other way. If x equal a is a solution, x minus a is a factor every time. Now, if this was x equal negative 3 would be a solution, what would be your factor? X plus 3. Very good. What would be your x-intercept? Negative 3, 0. Remember we say x equal negative 3. Yeah. You see, any one of these being true, all four are true. Okay? Real zeros of a polynomial function. We can call them zeros, we can call them solutions of the equation, we can call them factors, and we can call them x-intercepts. They're all related. First cousins. Okay. So let's look at example 3. Find all the real zeros of this polynomial function. How would you begin? All the real zeros of that function. How would you begin? Factor it, okay? And how would you, yeah, I'm sorry. You set it equal to 0. You're absolutely right. Do y'all want to stay green or go back to black? Let's go back to black. Set it equal to 0. Now what? You got it right. I was skipping a step. Now we factor. And what would you factor out? I'd take the sign with it. Negative 2, is that all you can factor out? X squared. And what do you have left? X squared minus 1. Very good. That's equal to 0. Now what does that tell you? Say again? Okay, I couldn't hear that. Okay, yeah, but what else what do you notice you can keep doing? Are you through factoring? No, there's more to do. Okay, this will be a minus 2x squared. Don't lose that. And this factors is what? X plus 1 times x minus 1. Now that's equal to 0. Now, I could be really silly here. No, never. Okay? And set each of these factors equals 0. We could do this. That factor is negative 2 times x times x times x minus 1 plus 1. I can't write. Times x minus 1. Okay? Equals 0. And set each one of them equal to 0 if I wanted to. Does that first one work? Minus 2 ever equal to 0? No, don't do that. Okay. All right. But then the next two, what would that give you? Say again? X equals 0 or x equals 0. Now that's silly to write it twice, isn't it? But, you know, that's true. And therefore we call this a double root. Or x equals 0 it's a 0 of multiplicity 2. There's 2 of them there. How about the next one? What does it tell us? X equal to negative 1 or x equal 1. Okay, what was the degree of that original thing? 4. How many zeros did it have? Okay, 4 if you count this one twice. But most of the time we don't count it twice. That's just 1, 2, 3. But remember, all it is at most 4 zeros. This one only happens to have 3. One of them has a multiplicity of 2. Okay? So it says, find all the real zeros. We did. Determine the maximum number of turning points. What would that be? 3. The maximum number of turning points would be 3. And I take it we must be out of time. Oh, how could it be? Okay. We will pick up then next time with, let me give you a few homework exercises. Yeah, I know you were yelling at me for not doing that. I would do all of 9 through 14. The odds are in the back. But do them all of those and look at the odds. Then I think you can do any of the, either 15 or 17 or both. Any of the odds 19 to 29. Either 31 or 33. And you can start working on 35 to 49. Okay. You are finished with it? Okay, let me make sure I got the correct score down then. Okay, yes, sir.
The research paper.
Excellent. Very good. Good topic. Okay.
I haven't even approved. I've already written the paper. So.
Well, no, it's too late now. I won't approve that one. Okay. No, that's fine. Perfectly fine. Let me put him in place before I lose him. Okay. Let me get your paper done. Test. Way at the beginning. Okay, I'm close. I'm really close. There we are. You got a good score. Did you see it? Okay. Oh, I already put you down. No, I didn't. That's somebody else. Okay, there you go. All right. You're not through. Okay. You want to continue now? Okay. I'll have to put you in a different room so it's too far. You're number 2, right? Okay. My work study student had to put 1 and 2 on it because he had to keep y'all straight. He didn't want to mix them up. That is your writing, right? Okay. All right.
I apologize for not communicating. I missed all last week. Just do the work.
Oh, I see.
I've been in Tennessee all week.
Yeah.
I was just.
Okay. Have you turned in your quiz?
I turned it all in.
You turned in the quiz? That's what I'm asking.
We took another quiz.
Huh?
We took another quiz after
No,
the
no,
test.
just the first one.
I turned in the first
You
one.
did. Okay, got it. That's all I'm asking. Yeah, you got it. So when do you want to take the test?
I started taking the test.
Oh, you did.
I
Okay.
finished on it. I believe.
When do you want to finish? Yeah, there you are.
I have your office times in my backpack.
Okay.
I gotta figure out a good office time and then try to coordinate with you on that.
Okay. Have you got now free? Do you want to work on it now, or you want to wait till later?
I would want to work on it now.
Huh?
I said I really do want to work on it now, but I have my computer science class.
Oh, okay. Yeah, yeah. I don't want to interfere with another class. Okay, get in touch with me. I'll be here till 8 o'clock tonight. So now I'll be in class the next 2 periods and then most of the afternoon. But come in, in between classes or whatever, and I can give you a test, put you in a different room, or during the office hours, I'll find the room close to my office.
You're not in the Birmingham campus today, are you?
No, I'm here all day today. It's tomorrow I go to the Birmingham campus after 2:30, something like that.
What time are you going to Washington? I don't want to.
I usually eat in my office, so you can come by then anytime between 12:15 and 3:15. I'll be in the office, and then after that, other than that, I'll be in the classroom. I'm in the office 3 hours, in the classroom 9 hours today.
I'll be around 2.
Okay.
I'll be there around 2.
Okay. All righty.
Thank you so much.
Were you going to work on yours now?
Yeah, I thought you had said you needed to go to a different room.
Yeah, yeah. Well, I think the room right next door is fine. I'm recording all this. Sorry. I forgot to turn this off.